last lecture, we talked about entropy, and we got started with looking at it. Today, we're going to look at, today and next lecture, we're going to look at the consequences of entropy, and in particular, we're going to look at a heat engine, a Carnot cycle, as a means of analyzing how those work. So for this, we're going to have two modes of operation. I'm going to draw this up on the board. So I have my system. Which is our engine. We want to talk about the Carnot cycle. And basically, we're thinking about the most efficient engine we can possibly build. And you think, well, okay, what's the most efficient way to do something? We're going to essentially have some way to put heat into the system. The system uses that heat to do work. And the most efficient way we can possibly do this is if we have some reservoir at temperature minus T2 and a certain amount of work, Q2 gets injected in, and then work is done. But that's not everything, because when the work is finished, there's going to be some leftover heat. So the next step is essentially, I was going to draw it separate. This is step one. Actually, step one and step two. I'll just draw it all together, and we can talk about it separately. First step is we inject heat. Second, we take that reservoir off, and we do work. Next, the leftover energy is ejected as heat into the reservoir at T1, and a certain amount of leftover energy to form heat is ejected. And then the system has to go back. So call this, let's call this work done, and then there's going to be a work to reset the system, because we start out at a given temperature, inject heat, and we're injecting this at a constant temperature. The system does work isolated from the reservoirs, so it's adiabatic work. No heat goes in. Then the leftover heat gets dumped into this low temperature reservoir, and this temperature is picked so it's the same temperature of the system. Right? When it does this adiabatic work, it changes temperature. And then we disconnect that. And then lastly, the system, and I don't know if you want to think of it as a piston type system, it has to be, well, we're going to think of it as that because we're going to use an ideal gas as our model. We have to push the piston back to go to the original pressure and volume in order to have a closed cycle. So basically, we need to have an expression then for our adiabatic work and for our isothermal change in temperature. Let's say isothermal expansion / compression. So basically in our temperature pressure diagram, in which we have V as a function of temperature and pressure. We got some surface, and we're traveling along some line on that surface of constant temperature. So we're moving from B1T to T. We're going to be working with an ideal gas. And that's just out of simplicity, but you'll see this generalizes, and we'll probably have to wait for the next lecture for that. So it's an ideal gas. We have T equals 0 because it's isothermal, and as a consequence of that, the change in internal energy is also 0, because we know that the internal energy is related to the heat capacity and the change in temperature. So as a result, U equals Q minus W, Q equals W. And if we say that this is a reversible process, and we're going to do that for all of these systems, we're going to say reversible. That tells us that W is the maximum work and Q equals the max Q rev. Using the language that we had in the last lecture. This max is equal to max is equal to the integral from volume 1 to volume 2 PV is equal to RT ln of V1. And because we have the reversibility of the work, we have delta S system is equal to Q rev over T R T over T V1 over V2 and delta S of our reservoir, so our changing notation here. Reservoir is equal to negative the Q rev T negative RT over T ln of sorry 2 over 1. 2 over 1. So delta S coat is equal to 0. Find reversible. Because that's how we started from the assumption. So we've got that, and then we got
a question.
Yeah.
Should there be a number of moles times LT?
Sorry, but you're right. Strictly, we should have that, but we're going to keep them constant. So going back here, we got I'm hoping is a marker that works, and adiabatic expansion and compression, which would be the second part. So by definition, Q equals 0, which means delta S equals 0, and it's reversible. And we had also that now P1 gamma equals P2 gamma. So basically in our temperature, pressure space, volume, is equal to, those two are equal to a constant, and we're talking about staying on the surface. On this, the surface defined by that. So those are going to be the two steps in our cycle. Let's write these out. Step 1, we have reversible, thermal, Q2, injected at T2. So constant temperature and heat's being injected. I know that's counterintuitive because all of us think that things are the same temperature, that heat doesn't transfer. And that's because we live in the real world, not in a reversible world. Because we think spontaneous means that there's going to be a change in entropy. That's just what we grew up seeing. But in this case, it's reversible. And as a result, we have two systems that are in thermal contact and heat is still being injected. Step 2. We now disconnect the thermal reservoir and we say that the system has a reversible adiabatic work. So there's no heat that goes in and out of the system, but the system will do work on the universe. And as a consequence of this, it changes pressure, volume, and it changes temperature. Temperature goes to T1. It changes state, but when it changes state though, it still keeps constant this pressure volume raised to the gamma. Step 3. The residual heat in the system gets dumped as an isothermal change in volume. Rev. So that's thermal. Q2 or Q1. extracted at T1. So when you think of this as a system, and you have some way of measuring the heat, so you know that you're getting exactly the residual heat out. And again, that's a little bit fictitious from our real world knowledge, but for the sake of us talking about these, we imagine that. Step 4, we have a reversible adiabatic work. And what this is essentially doing is it is resetting the pressure and the volume, because we want this to be an engine, meaning that after it comes back, it's going to go from the initial state around the loop and back to the final state. And in the process of that, the temperature changes to T2. So we've got the definition of the work in all these steps. So we could say, deviate from my notes, so hopefully I don't mess this up too much. We can say this is going to be W1, W2, W3, and W4. That's not a good way of doing it. Because I've got 1s and 2s here already, so let's do a different notation. Let's call this C, and WD. That's the work at each step. So the total work is WA plus WC plus WC. Sorry. In my notes, I'm using absolutes. D. And the total heat that passes Q2 Q1 because the process is cyclic, that means the initial and the final energy of the system has to go back. It's a state function. So Q equals W. And we define the efficiency as the work done per or divided by the heat that has to be dumped into the system. That is Q2 minus Q1 over Q2. And this is defined as the Carnot efficiency. Right, so we basically created a system in which all the processes are reversible, so there's no change, no net change in entropy.
So there's no change in U, right?
So no change in U, yeah.
Zero.
Oh yeah, sorry. Oh, cyclic therefore 0. Yeah. So no change in internal energy of the system. What this represents then is pressure, volume, space. The system volume T2 Q2. T1. This is T1. And Q1 being ejected here. Q equals 0. Then reset. So I'm going to 1, 2, 3, 4. This is T1, T2, Q equals 0. And our work terms V, so we're looking at really the area inside this curve. And I mentioned last time that anytime we have a closed, anytime we talk about work, we talk about work in terms of a force and conjugate distance or pressure, conjugate volume. In this case, PV, you can have any term you want, but when you have a paired set of parameters that give you work, if you make a loop inside that, the area inside the loop is either the work done by the system or done to the system. So in this case, we're saying that heat goes from a high temperature reservoir into the system, does the work, and gets dumped. So work is being done by the system. We can do the opposite direction, and we can pump heat from the low temperature reservoir to the high temperature reservoir. But if we do that, then we're putting work into the system. So if we go this way, we're doing work. If we go this way, then the work is being done to the system. Is that okay so far? Okay, so let's talk, erase this. Some of the implications of this. One of the other implications is that our efficiency is defined Q2 minus Q1 over Q2, and that's equal to 1 minus Q1 over Q2. Right, just change the range of the math. And we can take it and arrange that more, and we can say Q1 over Q2 is equal to some 1 minus the efficiency. Let's call that some function. And it's a function of T1, T2. Because these are the heat that's injected at constant temperatures. Just capital T's. My handwritten notes, I put lowercase t's. Again, for reasons that are not entirely clear to me right now. So we'll have T1 and T2. Because those are the temperatures where we have the injection or removal of heat. The other thing that's worth noting is that where we have this, we could have also taken a different path, right? So we could have said, okay, well, I'm going to perform a work, but only this much work is going to be done. And then I'm going to go back here and then go up. So I can have this loop, or I could have a system that has, it starts here, goes down, down, like that. The net work done by these two systems is equal to the work done by that single system, which means that I can have define this as P3 and Q3. And this changes my notes, but let's see if we can do this anyhow. So I've got this engine, which I'm going to call engine 1-3, and I've got engine 2-3, and engine 3-1. If I have that, then I'm going to have a Q, red. So I've got Q1-2, 1-2. I've got Q1 over Q3. Let's get rid of that. Just to make it easier to see. Okay. So I got 1-2. I've got Q1, Q3 as a function of T1 and T3, and I have Q3 over Q2, which is a function of T3 and T2, right? I'm looking at the efficiencies for the total and these two sub-engines. Okay. I'll get through this page and then we'll go to the quiz. Okay, so I can take Q1, Q3, and divide it by Q. Q1-2 divided by Q3, Q2, which is equal to Q1 over Q3, which I have here, which tells us that F T1 T2 over F T3 T2 into F T1 T3. Okay, and this, remember, is still the definition of 1 minus efficiency. These functions are functions of temperature. Well, you know what? I messed up enough with the notation in my notes and on the board, and we have very little time, so let's take the quiz. I'll clean this up and post correction to that.